Hello everybody and welcome to my presentation today for Eurosteel 2020 or 2021, which will be on the behaviour of rectangular concrete-filled tubular flange girders under combined loading. I'm presenting this work today on behalf of my former PhD student, Dr. Rana Al-Dujele, who finished her PhD last year, and this was a part of that research project. So the focus in today's presentation, as I said, is on rectangular concrete-filled tubular flange girders. We've also done work on different shapes under different loading scenarios. Today I'm looking at combined loading, so that's bending together with axial load. I should also say this is my third attempt at recording my presentation, and I think I've decided I'm going to keep going with this one no matter how bad it is. So bear with me if there are some stumbles along the way. Okay, so let's start with what is a concrete-filled flange girder. So these are relatively new structural solutions which comprise a steel beam in which the compression flange has been replaced by a hollow section which is then filled with concrete. And these types of girder are particularly useful in heavily loaded structural scenarios. So where we have a bridge approach, for example, or a ramp in a car park would be another example. Heavily loaded scenarios where standard girders don't give us enough strength or particularly stability. So first, an overview of what I will be talking about today. So I'm going to start off with a little bit of background on these members and how they have evolved. Move on then to the development of the FE, finite element analysis model, which we developed to analyse their behaviour. We also looked at an analytical model, which I will briefly introduce, and then some results and discussion, and hopefully some questions as well. Okay, so before the concrete-filled tubular flange girders came about, the first incarnation really were hollow tubular flange girders. So these were regular beams which had typically both the top and bottom, so the compression and tension flange replaced with a hollow section of any random shape. So there were, as you can see here, triangles, rectangles, circles. And really the purpose, or the motivation of using these sections was not just strength, but lateral stability. From there, probably a natural evolution was to fill the compression flange hollow section with concrete to give even more stability laterally and also strength, of course. So here we have a couple of images of real tubular flange girders used in real bridges. So these are from images from 2008, bridges which were in China, I believe. So looking at a circular flange at the top as well as a rectangular flange at the top. In fact, the bridge on the right-hand side also had a concrete-filled tension flange. There are a few advantages to using these members over standard sections. The main advantages, of course, are that this type of section provides greater strength and stiffness and lateral torsional stability compared with a regular I section made using the same amount of steel material. The second key advantage, is that the vertical dimension of the tube reduces the web depth, so you get less of a web slenderness effect in your beam. And there are generally fewer cross frames and stiffeners required in the construction. Moving on to the next slide, here we have a couple of more nice examples of these types of section used in real bridges. So the first one is the Lynch Village Bridge in the USA. And then we also have some rectangular tubular flange girders which were used in a bridge in China, which I will not attempt to pronounce for fear I get it wrong, I will surely get it wrong. So looking at the objectives of our work, our objectives really were to understand how these members behave. Previous work has looked at how they behave under bending conditions. In today's presentation and the work which has gone into it, we're really looking, as I said, at the combined loading scenario. Our aim was to help engineers to design these members. So we proposed and will propose analytical expressions which are suitable for design. We developed an FE model. Testing these specimens is just not feasible with the facilities we have, but also the cost would be enormous and the amount of load required would be enormous. So we developed an FE model, validated it as best we can, as I will discuss, and then looked at some of the influence of key variables, etc., on the behaviour. Okay, so looking at the numerical modelling, we used Abacus, as I'm sure most of you are very familiar with, the implicit dynamic analysis method. We included both geometric and material nonlinearities in the analysis. The steel, I do have a slide, I think, later looking at the steel model that we used, but the material itself, the section itself was modelled using a shell element. We ultimately ended up with a bilinear elastic linear strain hardening material model, having done a sensitivity analysis on lots of different types of steel models. And that one gave a good combination of accuracy and efficiency. The concrete was modelled using solid elements, and we used the concrete damage plasticity model to simulate its behaviour. So we validated it using the only test data we had for concrete filled tubular flange girders with a rectangular compression flange. And there were some tests done a number of years ago by Muteb, and these specimens were loaded under 4-point loading. So we replicated that in our model. So like I said, we had solid elements for the concrete, shell elements for the steel, and we did a mesh sensitivity study, of course, to make sure that we were getting the best combination of accuracy and efficiency. And we included imperfections in our analysis of the rectangular concrete filled tubular flange girders. So here we just have an image of the deformed shape and, of course, the initial undeformed shape. So as I said, in terms of the steel, we did actually look at using multi-stage material models. We looked at using non-linear material models, even almost exactly replicating the stress-strain response of steel. But in terms of the accuracy and efficiency and trying to optimize everything, actually the bilinear stress-strain curve, as shown here, was found to give quite good results. So we went with that for most of our analysis. For the concrete we used, here is the stress-strain curve for both the confined and unconfined concrete as used. So to correspond with the Muteb tests, the support and loading conditions were exactly simulated. So it was 4-point loading, simply supported end conditions as shown here. And there is more detail on all of this in the paper. So load deflection was the main response that we were looking at in terms of our validation. Here you can see the experimental response together with our finite element analysis response, and both were found to match pretty well. We were pretty pleased with this, and we did this for all of the tests. I'm just showing one for brevity today, but we felt like we were able to get a good representation of the real performance from our model. So then from there, we used the model to look at the influence of different parameters. I don't have it here today, again, simply for time reasons, but we did look at validating the combined loading. So we didn't have any test results on rectangular concrete filled tubular flange girders, but we did on large eye-shaped girders. So we looked at some tests and we did simulate the combined loading and validated that side of the performance. Not ideal. I mean, obviously in an ideal world, we would have some test data from these members under combined loading, but in their absence, we felt we did the best we could. So here are some of the interaction curves that we developed for lots of different scenarios. So looking at different parameters and varying things like tube diameters, material strengths, all the information on this is in the paper. I won't go too much into it now, but we generated these interaction curves where we could identify the relative influence of these properties on the response, and particularly looking at that interaction of the bending moment and the axial force, so how that was different for different geometries and material properties. In general, all of the members that we looked at behaved well. There was no sudden collapse of any structural component, and failure was generally gradual during the simulation. So a general conclusion is that the moment capacity, of course, as you would expect, is reduced when the axial tensile force is increased. So it's just a case of taking that into account in design. So we took those results and developed an analytical model, as I said, which was really focused on design, so design of these members and trying to enable engineers to actually be able to design them if they want to use them. And this model was based on fundamental mechanics, so looking at predicting the load capacity and the axial capacity to some extent of these members under combined sagging moments and axial tension. The interaction expression as shown must be satisfied in design. And it gives pretty good results, as you can see here. There are a couple of limits on some dimensions which we propose, and again, more on this is in the paper. So some of these outliers that you can see are when the tube is too big and the web becomes too tall, basically. So you get different types of behaviour governing the design. Okay, so a few conclusions from this work. Most fundamentally, these sections are really quite useful for very heavily loaded applications, and they're well able to take large moments and combined axial forces without encountering LTB issues. Of course, the moment capacity of a rectangular concrete filled tubular flange girder is reduced when you have relatively high axial tensile force, as you might have in some of the scenarios where these are likely to be used. So I think that's quite important to think about. And also, the developed nonlinear FE model that we used is a useful tool, a very useful tool for the assessment of the nonlinear behaviour and the failure modes of these members under this combined loading scenario. And thank you. So I will welcome any questions, hopefully in person. Thank you very much for your attention.